Good afternoon and welcome to the second part of our celebrations today. It is our annual Symposium of I²CNER, and I'm privileged here to initiate this symposium by giving you a general overview of the I²CNER research activities. And after me, you will hear our distinguished keynote speakers, and then you will hear just a sample of our research activities due to the minimum time that we have till 5 o'clock. So today I would like to talk about what I²CNER is, what we've done so far, what we managed to achieve. And I'd like to have a title here, Powering the Future, Internationalizing Research and Reforming Academia by following the spirit of the WPI program. Again, we are a WPI institute, and the pillars of the WPI program is to establish an international research environment. You've already seen it today. We are the United Nations. Almost everybody from all over the world is here at the I²CNER building. Advance cutting-edge research, reform the university system, reform the academic systems by bringing a more of an international dimension. I²CNER came into existence from a long collaboration between Kyushu University, which is a world-class academic environment, which has the best funded, best equipped facilities in the area of hydrogen research. The Hydrogenius Institute is a unique institute in this Ito campus, which, by the way, you can see it by taking a 10-minute walk down the road. And, of course, the University of Illinois, which is an institution with many years of tradition and impact. In order to understand where I²CNER fits in the entire Japan energy policy, here I try to summarize what are the main points of the Japan energy policy, and I took this from a presentation that our program officer, Professor Kazagi, gave. As you can see here, the energy policy is that facilitate renewable energy introduction. I²CNER is all about renewable energy. Clean and efficient use of natural gas and coal. I²CNER promotes CO2 management and mitigation. Greenhouse gas emissions, this is the target that Japan had, slashing emissions by 25%. As we've read in the newspapers, this is something that is very difficult to achieve. The Japanese government has decided that we have to revise this. I²CNER is here to help the government of Japan toward this mission and objective. So I²CNER essentially tries to address these types of issues that are main kernels of the energy policy of Japan, and this picture here gives us what is the mission and vision of I²CNER. In other words, to contribute to the creation of sustainable and environmentally friendly society by conducting fundamental research on advancing low carbon emissions and also capturing CO2 or turning into a useful project. At the same time, because we are an academic institute, we want to internationalize the university. We want to promote an academic environment of research that thrives on global cooperation and collaboration. Here are the 4 pillars on which this building is supported upon. It is research, fusion, internationalization, reformation. This picture here is a timeline that our energy analysts within I²CNER gave me, and this slide here represents new and advanced technologies that are going to be introduced in the Japanese energy markets, and when, with a targeted carbon reduction emission of 40 to 60% by the year 2050. In red are the I²CNER research projects. For instance, Japan is expecting to commercialize the fuel cell vehicle year 2015. The popularization of the fuel cell vehicle is expected 2030. So there is an I²CNER technology here. We are working on the hydrogen storage tank. It is an area that we believe will impact the future energy of Japan with a targeted reduction emission here. Our vision in the case of the transportation sector is a sustainable cycle, as you see it here. It is, we take hydrogen from the sun, we use photocatalytic water splitting, we create hydrogen, we transport the hydrogen, we store the hydrogen, we research on next generation fuel vehicles. And because photocatalytic hydrogen production may be a long-term project, we are interested in exploring other means of producing it. And because we want to have those means to be carbon neutral, we also try to explore how we can sequester any CO2 byproducts. So as you see, I²CNER is an institute that is issue-driven. Our research is fundamental in nature, is supporting technology. In other words, we put our emphasis on technology-driven fundamental research. This is our way of addressing the future. In the case of our research agenda, we are organized in thematic research areas. This is a very busy slide that essentially shows how we are researching toward addressing these carbon neutral technologies. We have a thematic research area, a division as we call it, on CO2 separation and concentration. We have one in thermophysical properties. We try to understand the properties of gases, high pressure, high temperatures. We have hydrogen structural materials. We try to understand how hydrogen interacts with structural materials. We work on next generation fuel cells. We try to address issues of durability. We work on hydrogen production. I told you about photocatalytic hydrogen production, carbon capture and storage. We want to store energy. And of course, we are working on issues on catalysis, materials transformation, waste of energy in chemical reactions. These are thematic research areas that are not isolated. They have common threads. For instance, the issue of catalysis, as you understand, is an issue that pervades many thematic research areas, such as next generation fuel cells, hydrogen-compatible materials, because you have the catalytic reaction when hydrogen gets absorbed into the materials, or in the case of carbon, how does it interact with the sequestered, when it is sequestered, how does it interact with the saline water? At the interface, what types of chemical catalytic activity we have. So those are our thematic research areas, and those are our key researchers. As an institute, we rely on 24 key principal investigators that lead the efforts. As you see, this is an international team of researchers. It has, for instance, Dr. I²CNER from the Imperial College in the area of hydrogen production. It has Professor Kirchheim from the University of Göttingen in the area of structural materials, Professor Harry Tuller in the area of fuel cells from MIT, United States, Professor Zhang from Tsinghua University. So our main key researchers, as you see here, are international. And from here, I will try to show you just a sample of our research activities. Again, sample. Later, subsequent colleagues of mine will go in depth. You will see specific programs. Again, as I told you, we have photocatalytic water splitting research areas here, and we explore all aspects of this. We explore understanding fundamental science, what happens when sunlight hits a free surface, what happens when this new surface is a different material. We try to explore various materials, free surfaces and interfaces, and we are also working in the area of devices, how we can use the sunlight through a device concept in order to produce hydrogen. And as you see, we are doing this in a collaborative spirit. You see here faces from Japan and the United States working together in these areas. And as you know, one of the roadblocks for photocatalytic water splitting is hydrogen production efficiency in the visible light, which is almost less than 0.1%. Professor Ishihara, who is the lead PI in this area, recently came up with an organic dye that in combination with gallium nitride and zinc oxide gave us in the laboratory 2.7% efficiency, almost around 500 nanometers wavelength. This is quite a breakthrough, and we are continuing in this area. We also try to push these efficiencies higher by using organic photovoltaics. My colleague, Professor Adachi here, is using the control, as we say, of molecular orientation in layered organic semiconductors. And he is coming up with efficiencies that are quite high, almost 6.3%. This is an efficiency. If we push it to about 10%, then we may be able to talk about technology. So we are pushing the hydrogen efficiencies here through all fronts. Organic, organic and inorganic semiconductors. At the same time, here in the area of organic semiconductors, we came up with the third generation organic materials for LEDs, and this is work that was just published in Nature, and Professor Adachi managed to come up with 100% electron to photon conversion. Organic LEDs is an interesting topic because my energy analysis division just informed us that if we use judiciously organic LEDs in the United States, we can reduce the primary energy use almost by 2%. So this is something that we need to take notice. So Professor Adachi is leading the way here. In the area of structural materials, we are working and trying to mitigate the effects, the degradation effects that hydrogen has on the structural materials, because we need structural materials to transport hydrogen. And over here, I believe we are leading the world. Our team here, the University of Illinois team, and the Kyushu University is leading the world in mitigating the hydrogen degradation effects. Dr. Sommerday from the Sandia National Laboratories, who is leading this division, will give you an in-depth analysis of what goes on in this area. We are working in the area of fuel cells, and we work by using futuristic concepts. For instance, we try to understand the molecular catalysis for fuel cells, and my colleague here, Professor Ogo, is informing me that perhaps we at I²CNER are the first example of developed precious metal-free molecule cathode and anode. And this is something that I would like to draw your attention. I hope this will make news. This is something that I²CNER will be proud of pretty soon, I believe. At least this is what my colleague Professor Ogo is telling me. We are working in turning CO2 into a useful product. We have a wonderful collaboration between Professor Paul Kennis, who is the head of Chemical Engineering Department of the University of Illinois, and Professor Naotoshi Nakashima here at Kyushu University, and they are trying essentially to use sunlight to pass it through a chemical reactor, electrochemical reactor, and turn CO2 either into a gas, a useful gas, or into a fuel. And they are telling me recently they are ready for a publication, a nice publication, that they managed to achieve efficiencies 45% here. Remember, in order to go into technology, we need energetic efficiencies greater than 50%. Again, this is a project that is an emblem of American and Japanese collaboration, and pretty soon I'm expecting that we will have results here too. Another project that we are working, as you've seen here in the tour we gave you today, is CO2, properties of supercritical CO2. I believe we are perhaps one of the 2 universities here in Japan which are devoted on fundamental science about properties of CO2. There are technology-driven centers in Japan for sequestration, but here at Kyushu University, we are building fundamental science. Another example is we are building here science for monitor possible leakage of sequestered CO2. Here, one of my colleagues, Professor Sitasima, works with colleagues at UK for an experimental investigation of leaked CO2, CO2 that's sequestered on the subseabed, and then Professor Sitasima is checking out what is the distribution of CO2 2 meters above the seafloor or 50 centimeters above the sea level. So we are developing these types of capabilities. At I²CNER, as you know, we are a young institute. We are 2 years old, but this doesn't prevent us from garnering awards. Here, I'm proud to present to you 3 I²CNER researchers for having received the 2012 Sumiya Award. This award, in order to be given, it requires researchers from 2 continents. Here we have researchers, I²CNER researchers, from 3 continents. Professor Tuller from MIT, Professor Kilner from Imperial College, Professor Ishihara, lead PI of our Hydrogen Materials Division. The next topic that I would like to touch upon is that we are making fusion and interdisciplinary research center of our operations. As you've already seen, we are collaborating, we are bringing disciplines together, and you've seen upstairs, right, during the tour, that we have a whole system here, a whole system approach for energy production. In fact, capturing sunlight, storing it into a storage medium, feeding hydrogen into a fuel cell, and then getting back into the grid. So this is a concept that needs serious analysis because we need to analyze the various efficiencies here, the efficiency of the entire system. The optimal operation of the entire system doesn't depend on whether each component operates optimally. Sometimes one component needs to operate less optimally, and we try to understand how this energetic analysis needs to be informed by the technology involved here. This is a very interesting concept. Hopefully, pretty soon we will have results here too. Again, I²CNER is internationalization. Here I would like to read for you what the United States Ambassador John Roos said on December 4 last month. What I do worry about is that the people-to-people ties, the ties between our younger generations, if our younger generations don't know each other, then the bonds will get weaker. This is the message that Ambassador Roos gave to us last December in the meeting that we had at Tokyo, and indeed we are addressing this concern here at I²CNER. We are sending researchers back and forth between the US and Japan. Here is our 2 faculty here, Sitasima and Kitamura, standing next to the director of the Midwest Geological Sequestration Consortium at Illinois. Our young students here are here at Kyushu University working. They came here in 2011. They are here right now working at the labs, right now as I'm speaking. I²CNER is a project that impacted the activities beyond the engineering aspects, impacted the activities of the librarians at the University of Illinois and the librarians at Kyushu University. February 1st, we have here a presentation by our chief engineering librarians, Bill Misko, Mary Slembach, in collaboration with the Kyushu librarians, Amano and Omura. And these 4 people working together across the Pacific are going to give us a set of scholarly information services that provide enhanced access to a myriad of online information resources to us. It is going to be a wonderful tool for our I²CNER researchers. We can work together between the Kyushu libraries and the University of Illinois libraries. The librarians at both universities, they loved this project, and as they tell me, they love to search. This is what the librarians want to do. We, the researchers, love to find. The librarians love to search. And searching between Japan and the US, it was wonderful for them. So we'll hear them February 1st. Sandia National Laboratories. We are privileged here at I²CNER to have along with us Dr. Sommerday. Dr. Sommerday is in the audience. He is leading the structural material division within our institute. He is a fellow scientist of the Sandia National Laboratories, and he is working with us. So in other words, here we have another international components, not only with the United States academia, but also with the United States laboratories. We are not only an institute between the US and Japan. We are a world institute. There are prestigious institutes of Europe that are involved with I²CNER. For instance, we have relations with the Max Planck Institute in Germany. We have Professor Kirchheim working with us from the University of Göttingen. We have Professor Gockler from the ETS from Switzerland working with us. We are going to develop relationships pretty soon with SINTEF, NTNU from Norway. Professor Kilner from the Imperial College is working with us. Professor Zhang from Tsinghua University is one of our PIs. Peng Hydride Storage from the Dalian Institute of Technology is working with us. We are really an international research environment. We are very active. We are organizing symposia. This is a symposium we organized last March at the University of Illinois, Issues of Energy. It was a very successful symposium. We had world leaders addressing the problems of energy. We organized a symposium here at Tokyo on December 7 to showcase our carbon neutral technologies to the energy stakeholders of Japan. Here you can see our ambassador, Dr. Ruse, Mr. Yoshida from MEXT, and Dr. Gardiner from the Department of Energy. Speaking of the Department of Energy, here at I²CNER, we have aligned our interest in establishing a network of excellence with DOE laboratories. And again, I would like to thank our colleagues at the Department of Energy for the help and the guidance they give us so that we maintain a relevance of I²CNER vis-a-vis what is important in energy solutions. And before I close, I would like to thank the Kyushu administration, President Arikawa, who is helping us to get this project, to ramp up this project, to move it from a transient to a steady state. They promised us that we have a building in January 2013. Yes, indeed, we are here in this very building enjoying it today. So we have the Kyushu University behind us, and that is a good feeling that we are going to succeed. And before closing, I'd like a little bit to think in the future to show you some intricate issues related with the business we are doing, what we are addressing here. On this chart, which has been given to me by our energy analysis division, you can see that Japan uses about 17 hexajoules of energy in order to meet its electricity demands, transportation, commercial, residential, and industrial. 17 hexajoules. The US, it uses about 100 hexajoules. Out of this energy, let me focus here on the electricity. It uses primary 7.44. This is what it needs. This is what we get out. About 4 hexajoules of energy annually. And as you see, the electricity supply, right, is producing about 46 of the CO2 emissions. So this is a very big chunk of the CO2 emissions because electricity production essentially is based on fossil fuels here in Japan. So what I asked the Energy Analysis Division, can we do something here? Can we go away from the fuel, from the fossil fuels? Can we do something renewable? Of course, this is a big concept for Japan. It is very difficult because the renewables are not as easily available. And this is the table they came out. I'm not going to go into the details, but this is a table. This is a live table. We are not there yet, but this is a preliminary assessment that we can use renewables for the electrification of Japan. Remember, we need about 4 hexajoules in order to have the electrification of Japan, and those are sources. If a medium potential can be realized by getting electricity from all the renewable sources. So these are concepts that our energy analysis tries to analyze and help us. But they said, even if we say that we can realize this medium potential that will give us the 4 hexajoules, we need to develop cost-effective and efficient energy storage. Energy storage is the key concept for the use of renewables. So we are investing here in I²CNER in this direction. Hopefully next year I will know more about this, I will have more about this so I can show it to you where we are. And finally, we are thinking about the future. Sustainability is another issue. As you know, key elements like indium are used, for instance, for photocatalysis, but there is not an infinite supply of these rare earths, those rare elements, so we need to learn to use them sustainably, and in order to use sustainably, we need to somewhat get a radical approach from classical designs. In classical designs, we are thinking about optimal performance. We need to go away from that and also think about optimal recovery if we are to go and talk about sustainability. This is a concept, hopefully I will revisit again in the next year when we will have more concrete plans as how I²CNER will evolve. And I would like, before closing, to say that we were honored by Crown Prince Naruhito, who visited our campus here on October 1st, and as you see, he talked here with Professor Sasaki about fuel cells and fuel cell cars, and also helped refueling a fuel cell car. And before closing, this is our building, January 2013. I'd like to draw your attention down here. We have the so-called I²CNER CO2. CO2 means coffee and collaboration. This is something that we are doing it every day. 3 o'clock every day, we are out here in the hall as we were all sitting out for CO2, as we call it. Let's drink I²CNER CO2. So I thank you very much for your attendance.
I'm Dr. Harada, work for Kawasaki Heavy Industries. First of all, congratulations on the integration of the new research buildings. It is a great pleasure for me to hear these special occasions. Wishing a good collaboration with I²CNER, I would like to start my presentation. First of all, I'd like to introduce the Kawasaki Heavy Industries briefly. Kawasaki is basically a manufacturer of transportation equipment such as ship, motorcycle, aerospace, rolling stocks, and the others are plant infrastructure and gas turbine and gas engine and machineries. This is a part of medium-term business plan of KHI, which was published 3 years ago. The president, Mr. Hasegawa, explained that the KHI would promote the development of the CO2-free hydrogen chain technologies. And also he said, in the future, primary energy will be renewables, nuclear energy, and fossil fuel with CCS. Secondary energy will be exchanged between electricity and hydrogen, mutually matching case by case. I think you can understand the meaning of CO2-free hydrogen. We are aiming at becoming #1 manufacturer of hydrogen-related equipment. That is our company's policy on the hydrogen. I'd like to talk about as follows. First, what is a CO2-free hydrogen? And next, introduction of CO2-free hydrogen chain from the brown coal. And final, introduction of HyGrid concept. Firstly, I'd like to talk about the CO2-free hydrogen aids. We called it CO2-free hydrogen that minimized all CO2 emissions from production to utilization. There are various CO2-free hydrogen chain concepts which expand from overseas to Japan. For example, there are hydrogen from renewable energy, such as hydropower, wind power, or solar power, and hydrogen from fossil fuel with CCS, such as coal, natural gas, or oil. We have ever simulated the demand of CO2-free hydrogen in Japan. Assumptions are shown in this slide. Cost of CO2-free hydrogen is at 25 to 45 Japanese yen per normal cubic meter. CO2 reduction rate, you say, CO2 reduction rate is 5% in 2015 and 80% in 2050. Nuclear limit is a maximum 50% of total electricity. This simulation carried out before the nuclear power accident. Renewable energy limit is a maximum 50% of total electricity. CCS is impossible in near Japan. Simulation 6 for energy portfolio to minimize the burden of the Japanese peoples. This picture shows the result of simulation. If CO2-free hydrogen is available with a cost of 25 or 45 Japanese yen per normal cubic meter, Japanese energy portfolio of minimized national burden goes like this graph. Of course, there is no CO2-free hydrogen now. But as a result, we can find the strong needs and big potential of CO2 hydrogen energy in Japan. This picture shows the sequence of CO2-free hydrogen chain from the fossil fuels. At first, hydrogen is produced from the fossil fuel with CCS. Then the hydrogen is liquefied and stored and loaded to the ship, then finally transported to Japan. In Japan, the hydrogen is used for hydrogen car, fuel cell vehicles, hydrogen combined cycle power plant, fuel cells, cogeneration and steel making, and de-Sulfur at the oil refinery. CO2-free hydrogen can contribute a huge amount of CO2 reduction as alternative fuels. I will introduce the current situation of each demand of hydrogen in Japan. About fuel cell vehicles and hydrogen filling stations. Japanese major automotive companies made an announcement that they would bring fuel cell vehicles into the global market in 2015. And Japanese major gas and oil companies made an announcement that they would establish more than 100 hydrogen filling stations in Japan. Further future target is bringing more than 2.5 million fuel cell vehicles into the market in 2025. About steel making with hydrogen reductions. The steel industry in Japan agreed with the Japanese government to reduce CO2 emissions by utilizing the hydrogen in the next generation steel making process. They say the technology will be established by 2030 and industrialized by 2050. About hydrogen for de-Sulfur at oil refinery. At oil refinery in Japan now, huge amount of hydrogen is produced with the refinery process and consumed for oil desulfurization. Huge amount of CO2 is byproduced through this operation. Now, if we convert this hydrogen to CO2-free hydrogen, we can reduce the huge amount of CO2. About recent discussion for future energy strategy in Japan. After the earthquake and Fukushima nuclear power plant accident, CO2-free electricity nuclear will be expected. We are proposing the introduction of CO2-free hydrogen from fossil fuels. The points are low cost compared with the renewable energies. Massive and stable supply. Storage possible, we say. This is the concept of CO2-free hydrogen chain. Next, let me show the CO2-free hydrogen chain from the brown coal. KHI has studied CO2-free hydrogen chain from brown coal in Australia. I will introduce it. Hydrogen is produced by gasification of brown coal. Chain sequence is the same as where I mentioned before. We aim at operating the first commercial chain in 2025. We are speculating that more than 40 chains will be made in 2050. Incidentally, before this large chain, we are planning a small-scale pilot chain in 2017. I mentioned about brown coal. Half of the world's coal reserves consist of low-rank coal, such as brown coal and subbituminous coal. About characteristics of brown coal, it is high moisture, so low efficiency of transport. It is as well as conveying water. Furthermore, severe problem is spontaneous ignition at dried brown coal. So now brown coal is no transport, no trade, no price in the world market. This is one of the cheapest fossil fuels. We have conducted a feasibility study of this project in cooperation with Australian companies and the support of both Japanese and Australian government. We studied such as where is the location of the hydrogen production plant? Where is the location of hydrogen loading base? Which route should we take for hydrogen pipeline? Is CCS possible? How are the regulation about hydrogen in Australia? How much are construction costs facility cost, CCS cost. We went on with them. This picture shows hydrogen production plant, one of our results of the study. You can see the brown coal gasification plant and hydrogen refining plant. The amount of hydrogen production is 770 tons a day, and CO2 of about 4 million tons per year goes to sequestration. This picture shows hydrogen loading base and hydrogen carrier. You can see the liquefaction plant, storage facility, and loading place in far. Loading place in far. Hydrogen of 770 tons a day is liquefied, stored, and loaded to the hydrogen carrier. Hydrogen carrier can load the hydrogen of 11,000 tons per one time. In this case, transported hydrogen to Japan is 225,000 tons a year. Hydrogen cost of CIF is about 13 yen per normal cubic meter. This amount of hydrogen can operate fuel cell vehicles of 3 million, and it can reduce 5.7 million tons CO2 a year. Or hydrogen power plant of 650 megawatt, and it can reduce 3 million tons CO2 a year. It is a fast chain. If number of chains increase, we can reduce the cost. And we are expecting less than 20 Japanese yen per normal cubic meter towards 2050. I would like to introduce the possibility of CCS in Australia. This figure was published by Victorian State Government of Australia. Center of the concentric circle is the location of the brown coal mine. It shows that there is a large CCS site is next to brown coal mine. The distance is inside 200 kilometers. This picture shows was published by Victorian State Government too. Victorian State and federal government are promoting the carbon net project, which is a CO2 hub for CCS. Here is a brown coal mine. And existing power plant in Lateral Valley. They say that CO2 will be injected from the onshore in the first stage and will inject from the offshore in the second stage. We are going to construct hydrogen production plant and to collaborate with the carbon net for our CCS. There are 4 shortlisted projects of CCS flagship program in Australia. As you may know, Zero Gen was rejected in 2011, and Kori project in Western Australia was selected and put physical budget for the government in June 2011. And then Carbonet was selected and provided the first budget of the government in February 2012. In current, the Carbonet project is in a phase of detailed investigations. I spoke about CCS station in Australia. We are expecting a Carbonet project for CO2-free hydrogen production from brown coal. Finally, I would like to speak one more topic. It is HyGrid. So far, I spoke about CO2 hydrogen from overseas. We started to study about utilizing hydrogen from renewable energy and its storage in Japan. As you know, Japan does not have much renewable energies compared with other countries. For instance, capacity factor of wind power in Japan is at most 20%. But there are many places where it's more than 40% in overseas. Therefore, we are considering the hydrogen from renewable energy is transported from overseas. However, pure Japanese renewable energy are very valuable from energy security point of view, although if it is expensive. We have to use such hydrogen and electricity effectively making use of their characteristics. HyGrid study group aim at studying it. This picture shows the HyGrid Basic concept. It is possible for hydrogen to store large amount and long time. So it can contain long period of fluctuation of renewable energies, such as wind power. On the other hand, battery is effective in case of containing a small scale of energy and short period of fluctuation. So we have to construct a reasonable system in combination with hydrogen and battery. This shows energy storage cost. I mentioned that hydrogen can store a large amount of energy and can be used for a long time. For example, if we would like to increase energy storage capacity, we simply make a larger tank. But in case of converting from hydrogen to electricity, its efficiency is lower than a battery. That's the problem for hydrogen energy storage system. We have to study how to utilize the hydrogen as an energy storage. HyGrid study members are shown here. You can see the I²CNER is one of the members too. Finally, a summary of today's presentation are shown here. CO2-free hydrogen from fossil fuel requires a CCS development and hydrogen technologies. HyGrid needs renewable energy and hydrogen storage technology. I expect the I²CNER plays very important role for our project and those projects. Thank you very much.
And I would like to call our second keynote speaker this afternoon, Dr. George Crabtree, who is a senior scientist and distinguished fellow in the Materials Science Division at Argonne National Laboratory and distinguished professor of physics, electrical and mechanical engineering at the University of Illinois at Chicago. He has won the University of Chicago Award for Distinguished Performance at Argonne twice, and the U.S. Department of Energy Award for Outstanding Scientific Accomplishment in Solid-State Physics 4 times. He is a fellow of the American Physical Society, a charter member of Eiichi's highly cited researchers in physics, and a member of the United States National Academy of Sciences. Most recently, Dr. Crabtree was announced as the winner of the new U.S. Department of Energy Innovation Hub. So we are looking forward to his talk. Thank you, and the floor is yours, Doctor.
Wonderful, thank you. Dr. Sofronis, and thanks for the invitation to come here. I'm thrilled to be here. I'm thrilled to see the new building and everything that I²CNER has done. I'm impressed that the scientists moved in 4 weeks ago and we saw operating labs. This is really something impressive, so I congratulate Dr. Sofronis and others for this wonderful accomplishment. So I want to change the tone a little bit and talk about the distant future. Specifically 50 years from now, and I'll tell you why I chose 50 years in a couple of slides. But think about what could be. And I'm talking now, of course, about innovation and the role of science and discovery to find new ways, new energy technologies that we maybe can dream of now but are not practical, but may become practical in that time frame. So my messages are here. I want to talk about energy as determining the aspirations and the limitations of society generally. We think about energy, we use energy all the time, we think about it much less. I'd like to think about it for a few minutes. Then I want to talk about what kind of society we expect to have or would like to have in 50 years. And then make a direct straight line connection from that vision to the kind of energy infrastructure and energy availability that we have. In other words, what kind of society we have in 50 years depends on our energy decisions now. And then I want to give you my top priorities for energy and society in 50 years. Of course, everyone will have different ideas. By my telling you my ideas, I want to provoke you. So I want to start discussion, not prescribe solutions. So I hope there will be some discussion and some disagreement. And I'm going to look rather visionarily at the future, so things that you may think are beyond the pale, but I believe actually are not. And finally, this is the bottom line message. Discovery science is the low-cost engine of innovation for energy and society. Okay, so let's see, first of all, a little bit about energy. So everything that you see on the upper circle is energy in some form, and it permeates all of our lives. It permeates our personal lives, it permeates our city lives, civic lives, and our national lives, and certainly as a citizen of the world as well. So transportation, food, buildings, tall skyscrapers that allow us to live and have commercial businesses, medical technology, communication, and there are many, many more. So when energy is generally available, these kinds of technologies and our society thrives. When energy is in short supply because it's too expensive or because for geopolitical reasons there's a shortage, then society suffers. So the point of this slide is that energy is absolutely critical to our well-being, to growth, and to innovation. So why did I choose 50 years? Here's the graph that tells that. This is from an article by Stephen Chu, the US Secretary of Energy, and Arun Majumdar, which came out in last summer. And it shows the percentage in the US of primary energy supplied by various fuels. Wood, and you see there's a transition from wood in 1850 to coal around 1900 when it was king. Then oil and natural gas, the red coming up. The yellow at the top right is nuclear, starting to make an inroad, and renewables. If you look through a telescope, you can see a little tiny spot at the top, which is the renewables. And the point of this graph, one of the points, is that it takes about 50 years to change the energy system. That is a rather long time, and there are many things that contribute to that time scale. One is simply the time scale of old infrastructure wearing out and being replaced, so that takes time. Another one is the perfection of technologies when they're first introduced. Of course, they're not perfect and they're expensive and not as efficient as they will be, and they gradually get better. But it's a 50-year time scale, and that's time enough for science and discovery to work. So if you think about what the past few years, shale gas, no one expected shale gas to have the impact that it has had. It's been a complete surprise. And that's something that came about through technology. There is a science component, and as I'll tell, I think there's an even bigger science component with respect to shale gas to come. So normally when you look at the 50-year future, the conventional approach is to take the present, ask what could happen, what kind of improvements in efficiency and cost reductions could occur, look at the relative costs of technologies, and project 20 or 25 years out. Hardly anyone actually projects 50 years out. What will happen? That's the future, that's the present extrapolated. I would like to take a different approach. I would like to say, in view of the importance of energy for society, let's start with the kind of society that we want in 50 years, and then ask what kinds of energy technologies and innovations and discoveries do we need to enable that society. So it just turns the cart and the horse around. The point is, again, 50 years is long enough for energy R&D to work. So we'll steer the energy society nexus toward the strategic society that we want, instead of simply taking the energy advances that occur, that occur and living with them. So here's the kind of global society that I would like to have, and I think most of us can agree with many of these things, and this you may disagree. Rapid growth of developing economies. So China, Asia generally, India, Africa, these economies need to grow. Steady growth of the developed economies. If they don't grow, they will lose the quality of life and lose the advantages that they now have to the developing countries. So we want that as well. Aggressive pursuit of discovery, science, and innovation, because that's how you get growth. It's from innovation and new technologies that growth occurs. Rapid deployment of the innovative technologies. I think that goes without saying. Lively communication, trade, and exchange of people and ideas across national and regional boundaries, a kind of globalization that everyone should participate in. And that requires interaction, as we know, of course, in the scientific world. Interdisciplinary discussion and interaction is so important. And finally, a globalization of opportunity, so that every country and every region can participate in the technology, the economic growth, the social, and the cultural advances. So the shorthand for this is a vibrant, interactive, inclusive, and rapidly advancing global society. So if you take those as your guiding principles, you then ask, what energy outcomes do we need to achieve this kind of society? And I've chosen three. You can do this in many ways, but I think these three cover a lot of the ground. The first one is energy security. You have to know, every country has to know that it has a supply of energy, so that's adequate, that it's affordable, not too expensive, and we know what happens when energy becomes expensive, everything suffers. That's sustainable, so you can have this source of energy for a long time, 50 years or 100 years. And very importantly, that's predictable, so that I know that next year or 5 years from now, I will be able to get energy at a certain price. It may be a little bit higher than the price of today, but it won't be outrageous. And this is something that we have not had. The last 10 years especially, or 20 years, have seen lots of fluctuations in the price of energy. So it needs those things. And then the second outcome is a stable climate, because global climate change is very, very expensive. And the discretionary resources, after you pay, and I'm talking about the world here, after you pay for the basics, food, shelter, health, are limited. They are not in such plentiful supply. It's those resources from which we get the innovation, that we make the forward progress. It's also those resources that will end up having to pay for climate change if it occurs on a grand scale. So these two things compete with each other. And you need a stable climate then to ensure that there are enough discretionary resources for innovation and for society to move forward. So the bottom line, curb carbon emissions and avoid the human and economic costs of climate change. And the last requirement, economic development and growth. This is where we get the future. So we need to have enough resources and enough innovation and invest in the right R&D to make this happen. It's the natural aspiration of people and countries and the source of discretionary resources. So we need it, and that requires inexpensive, abundant energy. So those are the guiding principles. And I will now give you a few energy technologies and energy advances that will help to make these realizations come true. And I've divided them, so we're looking 50 years away. So some things ought to be rather predictable, and things that low risk, you ought to be able to achieve them. But in a 50-year time scale, you can start to get more visionary and think about things that are farther from reality at the moment. So as you go down this list, the things get more visionary. First thing that's already on the road, replace fossil with wind and solar electricity. We can do that now. It's just a matter of doing it. But it hasn't gone very far. The second category, on the road but not sustainable. And I would say that nuclear electricity is in that category. So there are reasons, environmental and fear of accidents, that keep us from deploying it on a wider scale. We need to, if we're going to make nuclear a player, we need to address those concerns. And the second one, shale gas. In the United States, it's rather abundant. We've been drilling with hydraulic fracturing to get shale, to recover shale gas. The U.S. seems to be ahead of most of the rest of the world. But if you look at the resources, they're there. There's a challenge. It's not sustainable, I'll say, because of the effect on the environment. But there are ways to address that issue. So if you can address these two concerns, here are two opportunities. And then things that are not on the road and are a little bit more visionary, mitigate carbon emissions. So we all talk about, and we heard already today about carbon sequestration geologically. There's another option that I would like you to consider, and that is turn the carbon dioxide into carbonate rocks. And it turns out this may be a little more feasible than you think. Then develop electricity storage for cars in the grid so that we can have both transportation and renewable energy on the grid enabled at a large scale. And the final one, make chemical fuel a sustainable energy carrier. And we've heard a little bit about that already. So the first one, wind and solar electricity, this is US-centric. But here, since 1980, is the penetration of wind and solar on the electricity grid. You can see wind outpaces solar dramatically because it's a lot cheaper, and the technology is more mature. This curve looks rather, it is rather steep, so 30% a year is the kind of the rate at which wind is increasing, and solar is not far behind. It's now in the US about 2% of the total electricity. But at the growth rates of 30% a year, I've taken 15% just to have a number, you would have 27% renewable electricity by 2030 at these growth rates, if you could maintain them. So it's quite possible. The challenge is the price is too high, so you want to get the cost down, and the efficiency, especially for solar, is not as high as you would like. Those are the science challenges. How about safer, higher performing nuclear electricity? So it's wonderful because it doesn't produce any carbon dioxide. However, the challenges are safety. There are accidents. It's 1960s technology, most of it, so we can do better. And what do you do with the spent fuel? So let's imagine that you wanted to deploy nuclear electricity. What would you have to do? You would have to change the efficiency from 35%, about, which is what it is now. There's no reason why you couldn't have 50% efficiency. That is, 50% of the energy of the uranium goes into electricity. So how would you do that? You'd operate at higher temperatures. That is a strain on materials. You get the higher temperatures by cranking up the neutron dose inside the reactor, so you have higher radiation damage. And at those high temperatures, or almost any temperatures, corrosive environments. So the problems are mainly materials, and those are problems that can be solved. We can make materials better than they are, let's say, in the 1960s, and better than they are today. There's another issue, and that's the spent fuel. So the idea of most countries for storing spent fuel is not unlike carbon dioxide. Put it underground. This is a cartoon of what would have been the Yucca Mountain storage facility. It's really just a tunnel in a hillside. It's about 300 meters below the surface to keep this spent fuel out of the rain and out of the weather. It's about 300 meters above the aquifer to keep it out of the water supply. And you hope that it just stays there quiescently for a very long time. If you don't reprocess the fuel, it can be hundreds of thousands of years, or even, some people say, even longer. If you do reprocess the fuel, and that's what this cycle up here is showing. So here's the mining of the fuel. You put it through the plant once, and at least in the US this is the case. And when it's about 4% used up, you store it. But you could get that 96% of the energy back out by reprocessing. So going around this loop a few times, and then what you have left to store is much less, somewhere between a factor of 4 and a factor of 10. So you can solve this problem with science. The problem of safety one has to address. It's as much a technology problem as a science problem. My feeling is that one can do that. We haven't seen that happen yet, but it's certainly within the realm of possibility. How about shale gas? Well, if you think about, first of all, the price of shale gas, here in the US, in some energy units, was about $12, the peak between 05 and 08. The average off the peak was about 8, and since January of last year, it's hovered between $2 and $4. So it's a dramatic effect on price, and that determines, of course, the deployment. And if you look at this graph from the Energy Information Agency in the US, quite a conservative agency. I've never seen a prediction like this. Shale gas goes from 23% in 2010 to 49% in 2035. And of course, it's a prediction. It may not be right. But the expectation is that shale gas was going to be abundant and cheap. And of course, from a carbon dioxide point of view, it's an advantage because it puts out about half of what coal or oil does. So when you look around the world, and the rest of the world hasn't really developed or implemented hydraulic fracturing for shale gas, but they could. This is just a partial. Everything in gray, we don't know, but everything in white or a color, at least there's some estimates of what the shale gas potential, what the shale potential is. And you see it's pretty evenly spread around the world. So unlike oil and even sunlight, which falls mostly in deserts, shale gas could be a globally available resource. But there's a problem, and here's the problem. It's the effect on the environment. Here's how you drill for shale gas, how you recover it. You drill down till you hit a shale seam, which may be rather narrow. You turn your drill horizontal, and you drill as far as you can in this direction to access as much of the shale seam as you can. And you may turn the drill 360 degrees so that, again, you get as much of the shale seam as you can. Then you put high-pressure fluids, some filled with sand. The pressure is high enough to fracture the shale. You can do that. There are no explosions here. It's just high pressure. And when it fractures, cracks open up. The sand grains go into the cracks and keep the cracks open when you then release the pressure, and that lets the gas come out. So it's a bonanza at first. In the first year, it's wonderful. A lot of gas comes out that you wouldn't have gotten otherwise. The rate slows down dramatically after the first year or two, and finally tapers off. You get only about 15% of the gas, which is in the shale deposit, out by this technique. So there are problems. The other, from the production point of view, there are problems also from the contamination point of view. So those fracking fluids, where do they go? Well, they might leak out of the shale seam and into the ordinary rock, into the water supply. There can be leakage of all kinds of horrible fluids on the surface, what you do with the water that you do recover, the fluids that you do recover. And these things need to be looked at. But the point I want to make is that there's a science challenge here. And let me frame it this way. There's a regulatory challenge here. We could simply regulate the shale gas industry and say, don't do anything that's going to harm the environment. Probably a good idea, at least in that direction. That's going to cost money for the regulators to watch, and it's going to cost money for the producers to change their ways. Wouldn't it be better to understand the science of how these cracks form and what happens to the fracking fluids within the cracks, and control it, understand it to the extent that you can control it, and simply eliminate the problem? Again, a little bit of regulation is needed, a little bit of motivation, but you would increase the performance of the technology. Instead of 15%, you could get maybe 30%, and you would decrease the threat to the environment, and the cost would be much less. So there is an opportunity using science and discovery to make shale gas much more acceptable. How about carbon dioxide mineralization? So we all talk about carbon sequestration, and we heard already today about that, and it's a wonderful opportunity, of course. There's another one, and if you think about it, it has some advantages. Take a look first at this graph in the upper right. So if you take carbon and combust it to CO2, the number there is 394 in some units. That's the energy by which CO2 is more stable than carbon. And that's, CO2 is very stable. There are very few things that are more stable than CO2. But carbonate rocks are, things like calcium carbonate, by another 90, roughly, of those units. So it means that the carbon dioxide locked up in carbonate rock is really stable. You get that feeling when you look at this graph, which says how much carbon is there in various reservoirs, while the atmosphere, 720 gigatons, the surface ocean, about the same number, is the capacity. The deep ocean is huge, and everyone says the deep ocean can handle all the carbon we can produce. Quite true. But carbonate rocks have even more, more than 1,000 times more than the deep ocean. So there's a reason why there's this many carbonate rocks. They're really stable in nature. So if this got covered up, the fossil fuel is, but you can see it's only 4 digits. So we could easily handle what the fossil fuel carbon dioxide emissions would be with carbonate rocks. What do you get? You get something that looks like this. You can use that to build buildings like this one, built from carbonate rock. Or you could backfill a mine or just some open space on the surface of the earth with carbonate rock and let it sit there. And since it's so stable, you don't have to monitor it. The problem, again, a science problem. Slow reaction kinetics. So it means you have to find a catalyst for it. And non-reactive coatings, the surfaces get passivated. Well, you have to control the surface chemistry. You can do that rather easily in a reactor on the surface of the Earth, much easier than you can, let's say, underground, where these same reactions take place, let's say, in carbon sequestration. But if you do it on the surface, you can really control it. So there's an opportunity. How about electricity? Here is a graph of the percentage of primary energy in the US, that is devoted to electricity. It goes from almost nothing in 1900 to about 40% today. And there's a reason for that. Here are some of the things you see, pictures of things that it does. It's really, really versatile. Here's the grid. So what's so good about it? It can take energy or power from almost any source. So nuclear, coal and gas combustion, solar thermal, hydro and wind, where there's no combustion at all, mechanical motion, so wind, or hydro, solar electric, you don't even need any motion or fuel cells. Send it through the power grid, and it can do a lot of things on the use side. Here are some of them. So it's remarkably versatile, and it can accommodate the old fossil sources or the new renewable sources. And once you get past this point, once you've made the electricity, it's really clean, it's really efficient. So the grid is about 90% efficient. Electric motors can be 95% efficient, so on. And it's really versatile. And here's the cartoon. The electrons go in on one side, give up their energy to the load, come back on the other side, and nobody knows they've ever been there. So it's completely neutral on the environment. So that's the advantage. That's why we like it. But there's one thing it can't do. It cannot store energy. Right now you have to use energy at the rate that you make it. Or it's actually the other way around. You have to make it at the rate that you need it for the grid. So there are two big opportunities for storage. One is storage that allows more than, say, the 2% penetration of solar and wind, which is now in the United States, and the world number is not very different from that. So if it got up to 20 or 30%, you would have to store it, so you could smooth out its peaks and valleys. And the second opportunity is drive your car on electricity, and the challenge is shown here. This is the Chevy Volt. the battery is almost as big as the car. And in order to, and this battery in the Volt, as it happens, has a range of 38 miles on a full charge. So you want to go farther than that. Of course, the Volt has a gasoline engine which gets you farther than 38 miles, but you need to do better. So it was mentioned, actually, Petros mentioned earlier that a new award was made in the United States to the Joint Center for Energy Storage Research, which we abbreviate and pronounce I²CNER. And the point of that, that's Argonne and 13 partners, will look at energy storage opportunities beyond lithium-ion. So lithium-ion is the most successful battery technology for the last 20 years, for sure. But we need to look beyond it because it probably can't give a factor of 5 higher energy density, which is about what you need to make cars and the grid and renewable energy on the grid viable. So here are some of the things. I won't spend much time, but there are 3 ideas. Lithium ion, when it goes back and forth, has 1 charge. It stores and releases energy. Why don't you use magnesium that has 2 charges, or yttrium, which has 3 charges, and double or triple, in principle, the energy stored? Instead of intercalation, which is what happens at cathodes and anodes in most batteries, certainly in the lithium-ion battery, why don't you use a chemical transformation? So lithium reacting with oxygen or with sulfur or sodium with sulfur, you can get higher energy density stored in those bonds, maybe a factor of 10 higher. And why don't you convert these anodes and cathodes, instead of solid materials, why don't you make them liquids so that you can store them in big tanks out on a farm somewhere? The footprint is large, but the cost is low. So there's lots of opportunity for science exploration here. The last thing I wanted to talk about was making chemical fuel a sustainable energy carrier. And I have 3 cartoons here, which are all taken from a recent paper. Hydrogen would do that, and we all know, especially this crowd, how sustainable hydrogen as a chemical energy carrier is. I put the date 2003 because, at least in the United States, that's a time when hydrogen was in high visibility. And what happens is, of course, the hydrogen comes out, reacts with oxygen, you get water, you come back, you have to split that water on the production side and reuse the hydrogen. There's another way to do it, and that is cellulosic biofuels. So here you use plants to do the regeneration. Again, you burn now the hydrocarbon. It's not hydrogen, it's a hydrocarbon. Produces CO2 and water, and you recycle both of those through various means, through the atmosphere or through processing the plants to reproduce the plants reproduce the fuel. So this is a completely closed cycle. As it happens, the best estimates, at least in the United States, are that you could get about 30% of transportation fuels this way, but not even 50% or 100%. There's another way, and that is carbon dioxide and water recycled not through biology, but through artificial means, taking, of course, energy from the sun or from the wind. And the advantage of this is, unlike the photosynthesis route that plants use, there are many routes here that you can use artificially, much more than just the photosynthesis. Some of them are shown here, never mind what's on there, but some of the things actually we heard about already today about making these reprocessing spent CO2 to fuel and using it again. So the final thing I want to say is about the cost of doing things. So it's an old rule of thumb, factor of 10, factor of 10. Whatever, if it costs you $1 to discover something, it costs about $10 to do the applied science, to develop it into what might be a viable technology. And it costs you about $100 to take from this step to commercial deployment. You see where the money is. And when you see it visually like this, it's really quite striking. So the point that I want to make is actually on the next slide. What about discovery science? Why is it so good? Well, the cost is low. It's the cheapest part of that cycle that you can do, and you can therefore afford to do it. In fact, governments can afford to do it. Governments really can't afford to do these 2 things. It has to be us, the consuming public, that ultimately funds that work through companies and so on. So the cost is low. It stimulates innovation. That's the lifeblood of economic growth. So it's very, very important. It tells you what will fail before you attempt to develop it. What a great advantage. I didn't do this. It would have failed anyway. You learn that from science and understanding materials and phenomena. It pays back far more than it costs. So economists will tell you that since World War II, about half of economic growth is due to innovation. That's a huge payoff, much more than it costs. And of course, it primes the innovation ecosystem. So the bottom line, which I'll put here, and I showed you on the first slide, discovery science is the low-cost engine of innovation for energy and society. So what I put here are just the things that I've already told you. I think I won't even go through this slide, but it's here. And I will point out, if you want to see a written version of this talk, it's on the web, been submitted to Futures. Here are the authors, and it's on our UIC Energy Initiative website, which you can get simply by searching. So thank you.